In this video, I'm going to demonstrate Metropolis sampling algorithm, which will draw samples from this distribution here on the left called f of x, and then display them on a histogram over here after the sampling with Metropolis algorithm. Okay, so Metropolis sampling, like I said before, is a method to sample from a probability distribution f of x. And so the steps in the algorithm are to first establish limits of f of x and the Metropolis step size. So we'll have x min, x max, and sigma sub s. And then the next step is to make a probability density function to sample from. And this could either be, in this case, we're using two normal distributions added together, but it could also be some sort of PDF that's based on underlying data. And so in Excel, we'll do this with the sequence, LAMBDA, and NORM.DIST functions. So essentially, we're going to define mu1 and sigma 1 for one of the parts of the distribution, and mu2 and sigma 2 for the other part of the distribution. And then we're going to put them together and plot them out. Then in the next step, we will start x sub t at a random value. And I'll just draw that from a uniform distribution between x min and x max. And in Excel, we will do this with the RANDARRAY function. Next, we will find a proposal for the next x sub t plus 1. And according to the Metropolis sampling, that will be drawn from a normal distribution with the mean at x sub t, so the previous step, and a step size of sigma s, so how far we'll actually move from the previous x sub t. And in Excel, we will do this with the NORM.INV and RAND functions. Drawing steps from a normal distribution is not an absolute requirement of the Metropolis algorithm. And in fact, in the more general Metropolis Hastings algorithm, that's made for many other kinds of probability distributions. But for the purposes here of this video, we'll draw from a normal distribution. Okay, so the next step will determine whether to accept the proposed xt plus 1 or revert to current xt. And first to do that, we'll draw a random value u from a uniform distribution between 0 and 1 to help determine that. And then we'll accept the new xt plus 1 if the following inequality is true. So on the inside here, it's the ratio between the proposed new value and the previous value. Or that either that or the minimum of 1 or that ratio. And that needs to be greater than or equal to u to accept the proposed new value. Otherwise, we will set xt plus 1 to the current xt. And that inequality helps move the samples toward parts of the underlying f of x that are more probable. And so in Excel, we will do this with the if, min, and rand functions alongside a custom bimodal function that we define in Excel using LAMBDA. And so in the final step, we return to step 4 for the next iteration to choose another xt plus 1 and then test it to see if we'll replace xt with xt plus 1. And we repeat that until the desired number of draws is achieved. And in Excel, we will do this with the sequence function and copying formulas down. And finally, after that is done, we'll create a histogram and observe the result. And it will look something like this in our example. And we can type F9 to keep regenerating the random values and see what kind of histograms come out of the different random values. With that overview out of the way, let's flip back over to the spreadsheet to get started. And here we see the bimodal probability density function that is our f of x for this sampling. I have created it as f of x in this column. I have my x values over here in this column. And then using trapezoidal rule numeric integration, I have verified that the area sums to 1. So to look at how this f of x is defined, essentially is these two NORM.DIST functions here in Excel. And it's not a terribly complex formula, but we're going to have to use it in multiple locations on the other sheet when we build out the full example. So what we're going to do first is create a LAMBDA function which will clean this up and make it easier to see what is going on when we use this repeatedly. So I'm going to make a new sheet and call it Metropolis. And the first thing I will do is zoom in so we can see it. copy over these values, which I'll use to configure the f of x on the other sheet. And then we can make our lambda function. So the steps to create a lambda function are to create it on the grid here and test it to make sure it works, and then create it in the name manager under the formulas tab. So here we go. It's lambda, and it's going to take one parameter, x, and then it's going to be 0.5 times NORM.DIST of x, and the standard deviation here, we'll have it reference that cell, or actually that's the mean, and we'll do the standard deviation, have it reference that cell, and then we want the probability mass function, and then we will repeat for the second part of the distribution. And then close the parentheses. Now, before I press enter, which will generate an error, I'm just going to test it at the value -7. And that gives me this value here. And that is the same as the first value we have on this sheet. Okay, with that test out of the way, we can create our lambda function. So I'm going to really quickly make a copy of it from here down to here. Control C. Then go into Formulas, Name Manager, make a new name, call this bimodal, scope it to the Metropolis sheet, and then I'm going to paste the lambda in here in the refers to. And we can see that there's our lambda, and we can close the dialog, clear the contents of this cell, because it's in the name manager. So to demonstrate how the lambda works, I'm going to make another plot of f of x. So I'm going to make a few columns here. I for the, to help calculate the x values, x, f of x. I'm going to use the sequence function to create 100 rows. Actually, 101 rows, one column. Start at 0 and step size of 1. So this will start from 0 and go all the way up to 100. So now I can make the x value, and this is, and bear with me, this is a somewhat unwieldy formula, but it will linearly interpolate between -7 and +7. So what this essentially does is the slope is these extreme values divided by 100, and then the x is times this I value, and that the intercept is the x min here. So that gives us -7 for the first value, which is good. And then it just starts increasing all the way down to the 100th row. And since I doesn't need to be shown in the sheet, I'm just going to hide it. Now, since we made our lambda function, it's going to be very easy to make the f of x. So it's just going to be equal to bimodal x. Let me clean up the formatting on that. And there we go. So now we can make a scatter plot with lines between the points, but not plot the points, so it's kind of a smooth curve. So I'm going to insert, go to scatter, the smooth curve version, select data, add a series. The series name will be that. The x values will be that. And the y values will be that. And there is our f of x. Now it's time to do the Metropolis sampling. So I'm going to need a few columns. T, x sub t proposal, f of x sub t plus 1 over f of x sub t. And finally, the accepted x sub t for that step. Okay, so then I'll make a sequence of t, and this can start at 1, but I'm going to have 10,000 rows. So I'm going to type in equals sequence 10,000. Make these column headings bold. And then for the just T1, I'm going to draw from a random distribution with RANDARRAY. So it's going to be equal to RANDARRAY one row, one column, min of over here, max of over here, and then I'm going to do false, so it returns a decimal. So there is our random x of t value that we will start with. And then just to note that this row is special because it's the first one, doesn't have all the other calculations. I'm going to fill it with a color just to remind us. Now, remember that the next x sub t is going to be drawn from a normal distribution centered on this x sub t, but with our step size of sigma s. Now, to first make our xt proposal, we're going to need to define a step size, which I'll call step size over here, and I'll just say 1. So a normal distribution with a standard deviation of 1. And now we can do NORM.INV. Probability is going to be equal to rand, mean of this, standard deviation of step size. And I'm going to need to fix that so we can drag that formula down. And so going from here to there is our proposed new step. And while I'm in here, I'm just going to format these a bit more nicely. Okay, so let's go ahead and do the part that decides whether or not to accept this new x sub t. This is going to be equal to binom, actually not binom, bimodal of this divided by bimodal of that. And then the next thing will be to insert the logic, which will choose the xt. So that's going to be equal to if the min of 1 and this number is greater than or equal to rand, then if that's true, we accept. And if it's not true, we keep the current. So we can see in this case that we accepted and are moving from this value to this value. And we can try a few different random numbers just to see different outcomes of that. I'm just typing in F9 here and look at how the steps might go. Okay, so the next step is to copy these formulas down. So just select this, double click it, and that makes 10,000 copies of this formula. And this one takes a bit longer, 10,000 copies of that. And 10,000 copies of that. So the last step will be to make a histogram. So I'm going to select the data. And I'm going to insert histogram. And it puts it all the way down here. So I'm going to cut it and then replace it up here. And I'll give it a title. I'll just say x sub t samples. This axis needs a little bit of work. I'm going to give it a number of bins of 100. And then reformat the numbers as numbers, decimal places 2. And that makes those bin intervals a bit more clear. And there is our first histogram. Okay, so this histogram looks a bit lopsided, but that could be because of the random number generation. So let's generate some more random numbers, again, with F9. That looks a little bit more symmetrical. And there we go. So looking at how the histogram changed is I changed the random number sequence. That shows that there is some randomness in this algorithm, and that's what it is built on. And one of the things I didn't cover up until now is the burn-in part of the sequence, wherein the first samples of the sequence of xt should be thrown out because they haven't converged on the right distribution yet. But anyway, if we just keep regenerating with F9, we can get different histograms like that. So this was a simple demonstration of the Metropolis algorithm for sampling a R9 distribution f of x. And where could you go from here? Number one, you could study the Metropolis Hastings algorithm, which can use other distributions to define the steps of the sampling. And you could dive deeper into the math formalism behind it. And I'll link a couple of resources in the description to do that. So anyway, thanks for watching.